Hello, in this video we'll learn about language modeling. Language modeling is crucial in modern NLP applications. It is the reason that machines can understand qualitative information. Each language model type turns qualitative into quantitative information. This allows people to communicate with machines as they do with each other to a limited extent. It is used directly in a variety of industries, including tech, finance, healthcare, transportation, legal, military, and government. Additionally, it's likely most people have interacted with a language model in some way at some point in the day, whether it be through Google search, an autocomplete text function, or engaging with a voice assistant. Language modeling is the use of various statistical and probabilistic techniques to determine the probability of a given sequence of words occurring in a sentence. Language models analyze bodies of text data to provide a basis for their word predictions. They are used particularly in NLP applications that generate text as an output. Language models determine word probability by analyzing text data. They interpret this data by feeding it through an algorithm that establishes rules for context in natural language. Then the model applies these rules in language tasks to accurately predict or produce new sentences. The model essentially learns the features and characteristics of basic language and uses those features to understand new phrases. Language models are used in speech recognition, which involves a machine being able to process speech audio. This is commonly used by voice assistants. Machine translation involves the translation of one language to another by a machine. Parts of speech tagging involves the markup and categorization of words by certain grammatical characteristics. Parsing involves analysis of any string of data or sentence that conforms to formal grammar and syntax rules. In language modeling, this may take the form of sentence diagrams that depict each word's relationship to the others. Spell-checking applications use language models and parsing. Sentiment analysis involves determining the sentiment behind a given phrase. Specifically, it can be used to understand opinions and attitudes expressed in a text. Businesses can use this to analyze product reviews or general posts about their products, as well as analyze internal data like employee surveys and customer support chats. Optical character recognition involves the use of machine to convert images of text into machine-encoded text. The image may be a scanned document or a document photo or a photo with text somewhere in it. On a sign, for example. It is often used in data entry when processing old paper records that need to be digitalized. It can be used also to analyze and identify handwriting samples. Information retrieval involves searching in a document for information, searching for documents in general, and searching for metadata that corresponds to a document. Web browsers are the most common information retrieval applications. Some common statistical language modeling types are n-gram, unigram, bidirectional, exponential, continuous space. N-grams are a relatively simple approach to language models. They create a probability distribution for a sequence of n words. The n can be any number and defines the size of the gram, or sequence of words being assigned a probability. The model then assigns probabilities using sequences of n size. Basically, n can be thought of as the amount of context the model is told to consider. Some types of n-grams are unigrams, bigrams, trigrams, and so on. The unigram is the simplest type of language model. It doesn't look at any conditioning context in its calculations. It evaluates each word or term independently. Unigram models commonly handle language processing tasks, such as information retrieval. The unigram is the foundation of a more specific model variant called the query likelihood model, which uses information retrieval to examine a pool of documents and match the most relevant one to a specific query. Unlike n-gram models, which analyze text in one direction, that is backwards, bidirectional models analyze text in both directions, backwards and forwards. These models can predict any word in a sentence or body of text by using every other word in the text. Examining text bidirectionally increases result accuracy. This type is often utilized in machine learning and speech generation applications. Exponential model, also known as maximum entropy model, is more complex than N-grams. This model evaluates text using an equation that combines feature functions and N-grams. Basically, this type specifies features and parameters of the desired results, and unlike N-grams, leaves analysis parameters more ambiguous. The model is based on the principle of entropy, which states the probability distribution with the most entropy is the best choice. In other words, the model with the most chaos and least room for assumption is the most accurate. Exponential models are designed to maximize cross entropy, which minimizes the amount of statistical assumptions that can be made. This enables users to better trust the results they get from these models. Continuous space model represents words as a non-linear combination of weights in a neural network. The process of assigning a weight to a word is also known as word embedding. This type becomes especially useful as datasets get increasingly large, because larger datasets often include more unique words. The presence of a lot of unique or rarely used words can cause problems for a linear model like an N-gram. This is because the amount of possible word sequences increases, and the patterns that inform results become weaker. By weighting words in a nonlinear distributed way, this model can learn to approximate words and therefore not be misled by any unknown values. Its understanding of a given word is not tightly tethered to the immediate surrounding words as it is in an N-gram model. Overall, these models generate statistical approaches from which more specific variant language models are derived. Model types may be used in conjunction with one another. In this lecture, we'll mostly be dealing with N-gram language models. So let's recall that N-gram is a sequence of N words. So given this example of a sentence with onions, please, we can extract some 1-gram or unigrams. These are one-word sequences. So for example, single words with onions or please. Then 2-grams or bigrams are two-word sequences of words. So for example, with onions or onions please. And 3-gram or triogram is a three-word sequence of words. So for example, our whole sentence with onions please is an example of a trigram. The definition of statistical language model is that it is probability distribution over sequences of words. So our goal is to compute the probability of a sentence or a sequence of words. The task that is closely related to this one is to calculate the probability of an upcoming word. For example, if we have a sequence of 3 words, we can calculate the probability of a next word given this sequence of 3 words. And the model that computes either of these, whether it be the probability of a sentence or the probability of a next word given a sequence of words, is called a language model. The language modeling problem starts with a training data set. From our training data set, or corpus, we define a finite vocabulary V of words. Here we can see an example. Then, given this vocabulary, we can build an infinite set of strings, V diamond, that contains all combinations of words from our vocabulary, each one ending with a special word stop. And given a training data set, we want to find a probability distribution that satisfies this equation. That is, the sum of probabilities of our strings sums up to 1. Each individual probability has to be greater than 0. So the question is, how do we estimate these probabilities of sentences? Given n training sentences, for any sentence of words x1 up to xn, we define C of a sentence as a number of times the sentence is seen in the training data set. So the naive estimate is to divide this count of a number of times the sentence is seen in the training dataset with the total number of training sentences. But the problem with this approach is that it cannot generalize to new sentences. In order to calculate the probability of a sequence of words, let's use the first order Markov process. So let's first define a sequence of random variables, x1 up to xn, where each xi can take any value from a finite set V, our vocabulary of words. And let's assume for now that the length of our sequence is fixed. Our goal is to build such model that can calculate the probability of our sequence of words, that is joint probability of the words. We can use the chain rule to write this probability as a product of terms. So the first term is a probability of the first word, and then we have subsequent probabilities. For I equals 2, we'll have this term P of x2 equals x2, given x1 equals x1, that is, we have the conditional probability of the second word given the first word. Then for I equals 3, we'll have P of x3 equals x3, given the first two words, which are x1 equals x1 and x2 equals x2, and so on and so on. For example, for I equals 4, we can write P of x4 equals x4 conditioned on 3 previous words, that is x1 equals x1, x2 equals x2, and x3 equals x3, and so on and so on. So depending on the length of our sequence, that is the number n. And then we can use the Markov assumption to make an approximation of this calculation. So we'll rewrite this equation by conditioning each variable only on one previous word, instead of conditioning on all previous words that appeared before a particular word. So let's write this approximation. So we keep this probability of a first word since there are no previous words. And then we write this following product terms. So for I equals 2, we have again the probability of the second word given the first word. Because here we have the same history as before. And then for I equals 3, we write P of x3 equals x3, given only the previous word, that is variable x2 equals x2. So we don't care anymore about the variable x1. And then for I equals 4, that is the random variable x4, we'll also care only about the value of a variable x3. So we'll no longer care about variables x1 and x2, and so on, times other product terms depending on the n. So we can write this generic form of a conditional probability of a variable given the history, so that we can approximate it. So we approximate this probability to a probability of a variable given only the previous word, that is the value of a previous random variable. When we want to calculate the probability of a sequence of words by using the first order Markov process, we'll condition each word on one previous word. But if we want to use the second order Markov process, we'll condition each word on 2 previous words. So if we want to calculate the probability of a sequence that is a joint probability of words, Then we write it as a product of the following terms. So first we have the probability of a first word times the probability of the second word given the first word, times the next product terms. Let's write a few of them. So for the I equals 3, we have the probability of a random variable x3 equals x3, that is the third word, given the first two words, x1 equals x1 and x2 equals x2. And the next term, so for the I equals 4, we'll have the probability of a x4 equals x4 given the two previous words. So given the variable x2 equals x2 and x3 equals x3, etc. So times the rest of the product depending on the number n. So we can rewrite this equation in a more condensed form by putting this product symbol at the front of our equation. So in this case, since we do not have any previous word before our first word, and before our second word we have only the first word, so we cannot condition on two previous words. That is the reason why we introduce here an additional special start symbol, star. So for compatibility reasons, we introduce these two additional terms, x of -1 and also the x0 equal to the start symbol. So we assume that each sequence starts with two stars and then is followed by the sequence of words. The previous two language models that are based on the first and the second order Markov process were using the assumption of the fixed length variable, but if you want to model a variable length sequences, and if we have n random variables, then we can introduce a special stop symbol that is not included in our vocabulary, set v. And if we define our language model such that the nth random variable takes the value of this special stop symbol, then we can use the same equation for the second order Markov process as before. So to calculate a joint probability of words, we can use this product of terms, product of conditional probabilities, where each word is conditioned on two previous words in order to obtain a well-formed distribution. We can now formalize trigram language model. So given set v, our vocabulary set of words, and a parameter q of w given u and v for each trigram, u, v, and w, such that w can be any word or a stop symbol, and u and v can be any word and also a start symbol. Then for any sentence sequence of words x1 up to xn, where xi is a word in our vocabulary, for I from 1 up to n minus 1 and xn equals stop, we can define the joint probability of n words as a product of q terms, where each q of xi is conditioned on xi minus 2 and xi minus 1, where each sequence actually begins with two stars, so x minus 1 equals star and also x0 equals star. Based on the trigram language model, let's now calculate a probability of an example sentence. So our sentence is a willow wiggles stop. So to calculate the probability of this sequence of words, we need to multiply the corresponding q terms. So we begin first by the first word, a, conditioned on first two star symbols. Then we multiply it with the next Q term, the probability of a word willow, given the star symbol and a word A, and times the next Q term, the probability of a word wiggles, which is conditioned on two previous words, which are A and willow, and times the last symbol in our sequence, that is the stop symbol, which is conditioned on two previous words that were willow wiggles. So the question is, how do we calculate these Q terms? How do we calculate the probability of a word conditioned on two previous words? The easiest principle is to use maximum likelihood estimate, which basically counts bigrams and trigrams in our training data set. So we can see the expression here for the Q term for the probability of a word xi given to previous words xi minus 2, xi minus 1. So we can see that in the numerator we count the number of trigrams that occurred in our data set, and in the denominator we have the number of bigrams that occurred in our data set. So basically this is the ratio which says which portion of these bigrams is followed by this third word. So to see concrete example, for this sentence or sequence of words, a willow wiggles. So if we want to calculate the probability of a word wiggles, given these two previous words, a willow, then we count the number of trigrams that occurred in our data set divided by the number of this bigram. But basically we can encounter the problem here. So for many words, for many bigrams and trigrams, it could occur that we have 0 occurrences of these trigrams, or maybe even possibly 0 occurrences of the bigrams. So we can pretty much tackle the problem of sparse data sets given two big vocabulary sizes. Our trigram language model might experience some sparse data problems, especially if our vocabulary is too large. So, for example, if the size of our vocabulary is n, then we have n to the power of 3 parameters in the model. So, for example, if n is 10,000, then there are 10 to the power of 12 parameters. To calculate the probability of a word given its context, we use maximum likelihood estimates. So, the trigram maximum likelihood estimate is basically the ratio of the count of trigrams and the count of bigrams in our training corpus. Then the bigram maximum likelihood estimate is the ratio of the count of bigrams and the count of unigrams in our training corpus. And the unigram maximum likelihood estimate is the ratio of the count of the number of times the word is seen in the training corpus and the total number of words seen in the training corpus. The trigram, bigram, and unigram estimates have different strengths and weaknesses. The unigram estimate will never have the problem of its numerator or denominator being equal to 0. Thus, the estimate will always be well defined and will always be greater than 0, providing that each word is seen at least once in the training corpus, which is a reasonable assumption. However, the unigram estimate completely ignores the context previous to words and hence discards very valuable information. In contrast, the trigram estimate does make use of context, but has the problem of many of its counts being 0. The bigram estimate falls between these two extremes. The idea in linear interpolation is to use all three estimates by defining the trigram estimate as follows. So the probability of a word given the two previous words is basically the weighted sum of all of the three maximum likelihood estimates, that is the trigram, bigram, and unigram maximum likelihood estimate, weighted with these lambdas. So These lambdas are additional parameters of the model which satisfy this equation. So the lambdas sum up to 1 and each lambda is greater or equal than 0. So the question is how to estimate these lambdas. So the answer to the question on how to estimate these lambdas is to hold part of our training set as validation set. For example, we take 5% of our data set to be the validation set, and then by using this validation set, we define, for example, C prime of a trigram as the number of times the trigram is seen in this validation set. And then we try to solve the following optimization problem. So we define this function L of the parameters lambda such that it sums up these product terms. So C prime, the number of times the trigram is seen in validation set, and the log of our Q term. So from previous slide, we used the linear interpolation to define these Q terms. So by using this equation, we can plug it in here. So we have the dependency on all of our lambdas, and then by using some kind of optimization technique, we can try to maximize this L function, which also corresponds to minimizing perplexity. It has been shown in practice that by allowing the lambdas to vary, we can obtain even better results. So here we have an example of a function that partitions histories. So the function pi of a bigram is defined as follows. So for the count of bigrams, that is 0, we define the value of this function as 1. So if the count of bigram is somewhere in between either 1 or 2, we define it as 2. So if the count is between 3 and 5, we define the value for our pi function 3, or in all other cases, so for big count numbers, we use the value 4. So when we recall our equation for linear interpolation, we can see here that it is slightly changed. So here we have these powers of lambdas defined with our pi function. So we can notice that here all the lambdas will be affected based on the function of pi. So by using this partition, we've obtained our goal, and that is that our lambdas now vary. In order to handle sparse data sets, we can use discounting methods. We can see an example here. So let's imagine that we have a data set in which the word "the" appeared 48 times. And then we have the counts of bigrams that appeared in our data set. For example, the dog appeared 15 times, the woman 11 times, the man 10 times, and so on, according to this table here. And then the problem is that some of the bigrams that occurred in our test set did not occur in the training set, so the probabilities would be 0. So to avoid this situation, by using the discount method, we can do the following thing. So we can take each count of a bigram and discount it. For example, by using this formula, we just discount it by 0.5. So here in our table, we can see this C star of X column, which basically indicates these new values for our counts. So if we want to calculate the maximum likelihood estimates of our bigrams, which are given in the third column, we can see here the values, but since these are the reduced discounted counts, we can notice that if we sum them up, they will not equal to 1, so this will no longer be a probability distribution. So we have now kind of missing probability mass, and this missing probability mass we'll use in order to cover these missing bigrams, and we'll put some of this probability mass to the words and bigrams that we have not seen in our training data set. The backup model by Katz shows us an example of how to handle missing probability mass. So let's first formalize it. So if we sum up maximum likelihood estimates but with discounted numbers and subtract them from 1, we'll get the value of the missing probability mass that we'll call alpha. And for a bigram model, let's define two sets. Set A, that is the set of all words that did appear in our training data set, and set B, the set of words that did not appear in our training data set. So our Q term for a bigram model will be for the words that did appear in our training data set. Those are the words from the set A. Those are the maximum likelihood estimates with discounted number of bigrams. And for the words that did not appear in our data set, so the words from set B, we calculate this probability in the following manner. So we take sum of the missing probability mass, but using this weight. So we have basically the maximum likelihood estimate of a unigram. So that is the reason for the name of this model. So it backs off from the bigram by taking the maximum likelihood estimate of a unigram, and in denominator we basically have just this normalizing constant. The trigram backup model by Katz again first defines the missing probability mass alpha, but now using the maximum likelihood estimate for trigrams, but again note the count star, which indicates that we use those discounted values. Then for a trigram model, we also define set A and set B. This set A is defined as a set of words that did appear in our training data set, in trigrams of our data set, and the set B are the words that did not appear in trigrams of our training data set. So accordingly, this Q term, a probability of a word given to previous words, is calculated by either maximum likelihood estimate for a trigrams if a word did appear in our training data set, or if not, then again we take some of that missing probability mass, but weighted with this QML, maximum likelihood estimate, but for the bigram. So again, it is divided by a normalizing constant. The best way to evaluate the performance of a language model is to embed it in an application and measure how much the application improves. Such extrinsic evaluation is the only way if a particular improvement in a component is really going to help the task at hand. However, running big NLP systems end-to-end is often very expensive. Instead, it would be nice to have a metric that can be used to quickly evaluate potential intrinsic improvements in a language model. An intrinsic evaluation metric is the one that measures the quality of a model independent of any application. For an intrinsic evaluation of a language model, we need a test set. As with many of the statistical models, the probabilities of an n-gram model come from the corpus it is trained on, the training set or training corpus. We can then measure the quality of an n-gram model by its performance on some unseen data called a test set or test corpus. So if we are given a corpus of text and we want to compare two different n-gram models, we divide the data into the training and test sets, train the parameters of both models on a training set, and then compare how well the two trained models fit the test set. Given two probabilistic models, The better model is the one that has a tighter fit to the test data, or that better predicts the details of the test data and hence will assign a higher probability to the test data. The perplexity of a language model on a test set is the inverse probability of the test set, normalized by the number of words, as shown with this equation here, which is equivalent to this. We can use the chain rule to expand the probability. So, as shown here, thus if we are computing the perplexity of W with a bigram language model, we get this equation. It can be concluded that the higher the conditional probability of the word sentence, the lower the perplexity. Thus, minimizing perplexity is equivalent to maximizing the test set probability according to the language model.